So today, so far until this lecture, we have been discussing, we have been introducing tools to study various geometry, and our discussion have been rather general. So today, I will be discussing rather specific geometry, and in fact, a rather simple one, which is a two-dimensional torus. So it's a surface of a donut. And so we'll be discussing various holomorphic and meromorphic functions on this two-dimensional geometry. It turns out that this is a rather deep subject, and it has lots of rich structure. The theory of these functions have lots of rich structure. And in addition, it has lots of applications to various problems in mathematical physics. It appears in the study of, for example, two-dimensional electron systems in condensed matter physics, two-dimensional conformal field series, understanding energy spectrum of two-dimensional field series, and also in string theory. So this will be understanding holomorphic and meromorphic function on torus will be very useful tool to understand this subject. And main players of these meromorphic functions that we'll be talking about is called theta functions. And in fact, on the very leftmost of the blackboard, if Jawon can move the camera there, you see that there are 4 theta functions like that. So we'll be discussing those in the second half of this lecture. But before we get to there, let me first discuss a general thing about two-dimensional Riemannian geometry. So we'll be considering a metric of this form. Now, this is a 2x2 matrix. This is a 2x2 matrix. But now, in 2 dimensions, of course, we can perform coordinate transformations. That has 2 components. 2x2 matrix has 3 components because it's symmetric 2x2 matrix, metric is. So we can make use of the coordinate transformation to remove 2 of the 3 degrees of freedom in the metric. So, for example, if you wish, you can diagonalize this metric. So you can choose coordinate so that the metric is of this form, where omega in general is a positive definite function of x and y. So metric can be chosen in this way, this diagonal metric. So if you like, we can write the metric in component like this also. Oh, by the way, this is a Riemannian metric, so it's positive definite. So it's diagonal and with the same eigenvalues. So we can always do that by local choice of coordinate. Now, once you introduce this kind of particular coordinate, we can also introduce natural holomorphic coordinate x plus iy, so that the metric now has become of this diagonal form. Can our friend in Caltech read all the way down here? Can you read this? Yes? Okay? Okay, very good. So now the metric is of this form, that with respect to these holomorphic coordinate, these components are 0. So you recognize that if you go back your lecture note maybe a month before, you may recognize that this is actually the form of the Hermitian metric, and moreover, it is scalar. This metric is scalar. And the reason for that is the following, that scalar condition in general is like this. So the Kähler condition is this, but in 2 dimension or in one complex dimension, this condition is trivial because there is only one coordinate. So this condition would have meant del z gz z bar minus del z gz z bar is equal to 0, but this is obviously trivial because these are the same coordinate. So therefore, this metric is Kähler. So from this we conclude that 2-dimensional Riemannian geometry is actually Kähler. So we are considering Kähler geometry in 2 dimensions. Now, today I will be interested in understanding. So this is not necessary. This does not. So we are not necessarily considering torus yet. We are considering general 2-dimensional geometry. We'll be interested in understanding particular class of functions, holomorphic functions, but in particular solution to the Laplace equation. So let me write down the Laplace operator. In general, the Laplace operator on the Riemannian geometry is of this form. But if you choose a metric to be of this form, then we can write this in this way, del z bar. So there are various advantages of using complex coordinate. One immediate advantage is that it is extremely simple to solve the Laplace equation. The Laplace equation now takes the form of del z bar of phi is equal to 0. Now, we can easily find a general solution to this equation, that is phi is a sum of holomorphic function and its complex conjugation. This is a general solution to this Laplace equation. So if you use complex coordinate, then solution we can write down, in the case of 2 dimension, a general solution to the Laplace equation. In the following, I'm going to set omega, this metric factor, to be equal to 1. But it doesn't, we don't have to do it. We can do all the discussions that I'm going to do today for general omega, but this will simplify some of our notation. So I'm going to stick to omega equal 1. Now, so this is a holomorphic. These are solutions to Laplace equation without a source. But you can ask, well, what about the Laplace equation with source? Suppose phi is some kind of electric potential, and suppose we introduce some kind of electric charge somewhere. Then you want to solve this kind of equation, but with the source term, delta function terms, on the right-hand side. Now, what can we do to find solution to such equation? Well, I would like to prove the following formula. Del z bar of 1 over z is equal to minus pi of delta function. This is 2-dimensional delta function at z equals 0. In general, of course, we can, if we want to have a source somewhere else, say A, we can just shift the denominator of this simple pole, location of the pole. Okay, so now let me try to prove this. Okay, so the proof involves the following fact that we have seen earlier. Namely, suppose omega is a one form. Suppose omega is one form, and then if you consider some 2-dimensional domain with d of omega integrated. Now we are considering 2 dimension. Omega is one form, d of omega is 2 forms, so we can integrate over some domain. Suppose it is some kind of disk on 2-dimensional surface. Then the Stokes theorem says that we can write it as an integral over boundary like that. Okay? So this is a Stokes theorem. So I'm going to use this to prove this theorem, to prove this identity. So choose omega to be 1 over z minus a dz. Okay? And then let's choose the integration domain here to include this point A, and then consider a disk surrounding it. D of omega, well, since we already have dz, d of omega is equal to del z bar of z minus a times dz bar with dz. Right? However, this dz with dz bar with dz, what is this? Well, this is d of x minus iy which d of x plus iy. So it is a simple algebra to show that this is equal to 2I times dx wedge dy, which is a volume form. Since we are setting omega equal 1, the volume form in 2 dimensions is dx wedge dy. So therefore we see that this is equal to 2I times del z bar of z minus a integration in this domain of dx wedge dy. So now we can perform. We can use the Stokes theorem to show that this is equal to 2I of contour integral of dz over z minus a on the contour surrounding a. Actually, if I use the Stokes if I use the Stokes theorem, I would have gotten minus sign, but then orientation would be in this direction, so I flip the orientation. So this is the correct orientation. So now, excuse me. So I'm going backwards. So I think I should be getting this sign. So then, if I use the Stokes theorem, then this is going to give you minus 2 pi with this orientation. So then I get minus pi. So by simply applying the Stokes theorem to this one form, one can show that integral of d omega over any domain containing A gives you minus pi. So in order for this to be correct, it has to be that this left-hand side is equal to minus pi times the delta function localized at z equal a. Okay? So this is sort of simple proof of this statement. So this means that if we want to solve Laplace equation, we can try to make use of this one. Namely, suppose, for example, we want to solve the following equation, that 4 pi of, following equation, that delta of phi is equal to 4 pi of delta of z minus w, for example. Suppose you want to solve the following equation, and let's call that as a Green function. So delta of g of x, sorry, what am I writing? Delta of g of z w is 4 pi delta of z minus w. Suppose we want to solve this equation. To make sure that where z is acting, delta is acting, let me write z over here. So delta z is equal to 4 times del z bar. Okay? So then we see that we can solve this equation easily by setting g to be equal to minus log of z minus w absolute value squared. Because if I take, for example, derivative with respect to z, this gives you minus z minus w, minus 1 over z minus w. So therefore, if I take one more derivative with respect to z bar, then I would get minus of del z bar of z minus w. But then we just prove that this is equal to minus pi. This is equal to minus pi times delta function. So this gives you what you want if you take into account this factor 4. Okay? So you see that, therefore, in 2-dimension, special solution to this Laplace equation with source is given by logarithmic function. Of course, we can add any holomorphic function to it or its complex conjugation, and we still have solution to this equation. Okay? But one thing that is very interesting to note is that this is a logarithmic function. So log behaves, as you know, like this. So if this is absolute, so if this is z direction, the log would behave like this. If I consider real section, for example, this is 1. So in particular, this grows as z goes to infinity, which is very different from other dimensions. We know, for example, in general, in dimension n greater than or equal to 3, if I solve the Laplace equation with a source at the origin, then the solution to this Laplace equation would be of this form. So for example, in 3 dimension, as you know that if you solve the Laplace equation with source in 3 dimension, you get 1 over r Newtonian potential or Coulomb potential. So in higher dimension, you have higher power in the denominator. So that means that as x goes to infinity, the effect of the source decays by power. This is very different in 2 dimension, where the correlation between the 2 points never diminishes, but in fact increases as the distance grows. So there is a very strong difference between 2-dimensional solution to the 2-dimensional Coulombic equation and its higher dimensional counterpart. And this is rather important. This gives you various distinct features of 2-dimensional physics compared to higher dimensional physics. For example, it was proven by Sidney Coleman that in 2-dimensional quantum field theory, there is no spontaneous symmetry breaking. Spontaneous symmetry breaking is a very important effect. In physics, it is responsible for superconductivity, for example, or the Higgs effect, which gives mass to elementary particles. But it was shown by Coleman that such effect does not take place for quantum field theory in 2 dimensions. And this can be traced back to the fact that the solution to this kind of equation does not have decaying correlations. You're raising hand or no? Okay. Okay. Any question? I think this was fairly simple. Yeah, that's something you might have learned in your undergraduate course of electromagnetism. Now, so this was local solution. But if we introduce some interesting topology for 2-dimensional surface, then we might need to do a little bit more. So for example, before we go to torus, let's first consider a cylinder. Suppose we are considering a geometry that is a cylinder. Well, you can obtain cylinder from 2-dimensional plane by just saying that suppose you start with this complex coordinate z, and then you periodically identify z by translation by 1. Namely, you consider 2-dimensional plane, so z is a coordinate of the 2-dimensional complex plane, and then you just periodically identify z and z plus 1. That gives you a cylinder. You can ask, what is the solution to Laplace equation on the cylinder? Okay? But now the solution has to have a periodicity because it's defined on the torus, cylinder, excuse me. So it has to be periodic in one direction, and also it has to have the property that when z and w is close to each other, it should behave like this with some other regular term where z is close to w. John, are you following are you able to follow the blackboard? Okay, are you looking at the right part of the blackboard? Do you see me?
No.
Hi, are you tracing the blackboard okay?
Yes.
Oh, okay. Don't fall asleep. That's your work, okay? You are paid for that. Okay, so this Green's function on cylinder has to have these two properties. One is periodic in one direction, and the other is that it has a singularity at z equals w. There are various ways to obtain such function. For example, you can consider summing over all the images. That may be something that you might have learned in undergraduate electromagnetism. Namely, you start with this kind of solution, the logarithmic solutions like this, and then you try to sum over its images. Image that is generated under this periodic identification. But in this case, actually, we can just write down the solution because we know that we know what a function that has periodicity, and we want the solution to be holomorphic plus anti-holomorphic except at z equals w. So that uniquely determines the function to be of this form. So instead of using z minus w, we just have to use sine of 2 pi z minus w. Clearly, sine vanishes linearly as z approaches to w. So when z is close to w, this behaves in the same way as this. And moreover, this is periodic in z, so it satisfies the desired property. Okay? By the way, this function behaves even worse compared to the two-dimensional Green's function in long distance. So for example, so what happens if you go toward axial direction in this cylinder? Well, in this parameterization, we are identifying z with z plus 1. So going toward, for example, the upper direction on the blackboard, going toward this direction along the cylinder, means going to the pure imaginary directions. So suppose I set z is equal to, say, I times x, and say try to take x goes to large. Well, what's going to happen? Well, sine 2 pi z is 1/2 of e to the iz minus e to the minus iz. So therefore, when z is equal to pure imaginary and it is very large, it's going to go like exponential. Right? So, there is a 2 pi here, I guess. So there is a 2 pi here. So that means that g would behave linearly now. When we try to go in this direction. So the previously in two-dimensional plane, the correlation grows like logarithm. In cylinder, it's even worse. It's linear. Well, you could have expected that from this general discussion I had earlier. Namely, I said that in n dimension, John Won, are you following the blackboard? Okay, good. Let me know whenever you lose me, okay? Okay? So Green's function grows in distance like this. I said that in n dimension, Green's function grows like that. So this linear behavior is just like n equal 1. Because if n equal 1, you have 1 minus 2, which is minus 1, so that means the Green's function grows linearly. And this is actually what one should have expected, because if you go long distance along cylinder, then the thickness of the cylinder becomes irrelevant. So the system starts behaving like one dimension. So that's consistent with this behavior. So n equal 2 is sort of special, because in that case it looks as though you get constant rather than logarithm. But in fact, one should get logarithm, because you can write this as exponential of n minus 2 times log of z minus log of x minus w, x minus y, I guess. So indeed, if you think that you are very close to n equal 2 dimension, you can expand it. You have 1 plus n minus 2 log of x minus y. So when you are close to 2 dimension, indeed Green's function behaves like logarithm. So this formula is rather universal in that sense. Okay, so we are talking about cylinder, and we see that it is given by sine function. Okay, now we go one more step. So here for the cylinder case, we periodically identified the two-dimensional plane in one direction, and then obtain the cylinder. Now we can consider going to the torus, which is the main subject of today's lecture, and we go to the torus by now periodically identifying in one more direction. Okay, so let's see, where is my note? 1, 2, 3. Okay, so it's here, yeah. So initially we periodically identified complex plane in one direction, so z is identified with z plus 1. Now to make torus, what we can do is take upper part and bottom part of the cylinder. First cut the cylinder into a piece like that, and then try to identify them. Say, suppose you choose the length beta, for example, here. And then we can try to identify the lower portion of this cylinder with upper portion of the cylinder like here. Okay? But one can do one more thing, which is that rather than straightforwardly identifying the top and the bottom of this cylinder, we can twist it by some angle theta. By that I mean the following, that identification can be done so that z is identified with z plus I beta, but we can also introduce some twist theta. So what we are doing in complex plane is this. So you have, so this is a complex plane, and this is a real direction, and this is imaginary direction. This is 0, this is 1. Now I'm going to introduce one more point on the complex plane here, which is theta plus I beta. And then, so here, I'm going to draw this kind of parallelogram. So this is theta plus I beta plus 1. And then what I'm going to do is periodically identify the sides of this parallelogram. This gives rise to a torus. Okay? So we can define torus in the following way. You start with a complex plane C, and then you just identify this by z going to z plus 1, but also z going to z plus tau, where tau is theta plus I beta. So let me redraw this figure. So this is real z direction, imaginary z direction. This is 0, 1. Here is tau. Here is tau plus 1. Periodically identify in this way. So this gives rise to a torus, two-dimensional torus. Okay, I'm gradually moving to the right of the blackboard. Okay, so now you can again ask what is the solution to this equation. Okay, we can again ask that question. However, now we are faced with the fact that we don't have a solution to this equation. We cannot solve this equation. We cannot solve this equation because this equation is inconsistent. We can see that this equation is inconsistent because we can integrate both hand sides over the two-dimensional torus. Well, if you integrate Laplacian of Green's function, Laplacian of this Green's function on torus, say, we can choose coordinates so that it sits within this cylinder, like within this parallelogram like this. Then, since this is total derivative, we should be able to integrate that integrate by part, and it vanishes. Because, well, we have this cylinder, but then if you do the integration by part, you get integral on the boundary. But since the boundaries are pairwisely identified, so you should get 0. On the other hand, the right-hand side of this equation is clearly not equal to 0. But 4 pi, so it's inconsistent. You can ask why we didn't have that program before, like in the case of cylinder or plane. In that case, it is okay. The reason for this is the following. One way to understand why there is inconsistency is to note that so let's try to understand what kind of program we are trying to solve. We are trying to solve some kind of electromagnetic program where we introduce some kind of point source, and then from that point source you have a sort of electric field emanating from. So we have some electric field emanating from it. If you are in two-dimensional plane, then this electric field can go to infinity, and that's not a problem. Now, if you are on cylinder, it's still okay, because if you are on cylinder, well, electric field is somewhat confined, but still it can escape to infinity. Electric flux can escape to infinity like that. It is sort of confined in one-dimensional direction. That's why the potential had this linear behavior rather than logarithmic behavior. In general, the difference on the behavior of the Green's function toward infinity has to do with how these electric fluxes are confined. But now, if you think about that way, then you recognize that this equation is not consistent, because now we are on torus. And then we try to solve this Laplace equation with source at W. So there is electric flux emanating from it. But where does it go? Since it's compact space, so it has to end somewhere. So without any sort of sink that cancels the effect of the source, this solution is not consistent. So there is a way to remedy this problem. So for example, we can solve this equation if we introduce a sink of the same strength. If you do that, then you can have electric field emanating from that, and then that can be absorbed in the sink, like that. Or we can introduce some kind of uniform, we can sort of smear this out and then consider some kind of uniform background to absorb this electric field. So that the only thing that we want to make sure is that the integral of both hand side vanishes. The integral of the left hand side vanishes by integration by part. So that means that the integral on the right hand side should vanish too. So for example, we can introduce some constant function over here to absorb this effect. Now integral of this is equal to 1. So that means that we can introduce something that integrates to 1 too. And since we know that area of this cylinder is equal to imaginary part of tau, because the height of this parallelogram is imaginary part of tau, and the bottom length is 1. So that means that if you subtract 1 over imaginary part of tau, then the integral of the right hand side also vanishes, so we can have consistent solution. So that's what we are going to do. Okay, so we want to solve this equation. So now what we need is a solution to this equation with the following property, that it is periodic in both directions. Not only in one direction, but also in tau direction. And the theta function that I wrote on the very left end of this blackboard, if you just can move your camera all the way to the left. So we have these 4 theta functions here. So these theta functions have this property that they are almost periodic, quasi-periodic in both directions, one direction and the tau direction. Okay, I'm going back to the other side of the blackboard. Okay, so how do you get that theta functions? Well, one way to try to get it is by using the method of images. But if you try to do that straightforwardly, you get divergences. And so you have to do a little bit of clever trick. But if you look at this table of theta functions that I wrote on the left end of the blackboard, you don't have to copy that. It's on my lecture notes. So if you print that out, you can you don't have to copy the blackboard. So anyway, so if you use that theta function, then I can write down solution. So here is a solution. Okay, so this is a solution to these conditions, that it satisfies the Laplace equation with a source, it's periodic in both directions. General solution to this equation, or unique solution to this equation, can be written in this way. Where this theta is a theta function that I wrote over there, let me just write down the series form of this theta function, just so that we have some idea of what that is. Where and then eta is q to the minus 1 over 24 product, and then this q is related to tau. Okay, so you see that the theta function is sort of something like a superposition of sine functions that we saw earlier. So remember that in the case of cylinder, the Green's function is like log of absolute value squared of sine function. So here in this definition of theta function, we are summing over various different sine functions so that the periodicity can be restored. Periodicity can be imposed in both one direction and the tau direction. This eta is called the Dedekind function. Whereas this theta is called the Jacobi's theta function. This Jacobi's theta function is almost periodic in both 1 and tau direction. So that gives you this Green's function that is periodic. But it is not totally periodic. In fact, so let me write down the periodicity property of theta function. So it is in fact periodic with sign in one direction. So it is minus of theta 1 of z tau. But that's okay because here I'm taking absolute value squared of the theta function. So even if theta changes sign when z goes to z plus 1, it is okay. It is a little bit more problematic. Its behavior is a little bit more problematic if you look at the behavior of z goes to z plus tau. Because there, it is not only sign, but you also have various factors in front. So theta is not totally periodic, but it gives rise to a factor like this when you try to shift the variable from z to z plus tau. Since I'm taking logarithm of this, so that means that this term would give rise to some factor which is a log of this factor. You can see that that factor can be cancelled if you introduce a function like this. But this function is not the sum of holomorphic and anti-holomorphic function. So therefore, this is not annihilated by delta when acting on the Laplace operator. And in fact, this gives rise to this factor here that I introduced to absorb the electric flux. So somehow, the logic is that you try to solve this equation, first ignoring this 1 minus 1 over imaginary part of tau part, and then the theta function is the best you can do. But then it's not totally periodic. It should not be totally periodic because I have already argued that this equation is inconsistent. You can remedy that by adding this kind of term, but this term is exactly responsible for giving rise to this second term. So things sort of work out consistently. That is that periodicity on torus requires this introduction of this sinc term. Okay? Any question? That's clear? Okay. So now let me discuss one more interesting subject which has to do with geometry of torus, which is a modular transformation or modular invariance. So I'm going to the left side of the blackboard if John can follow me. So let me discuss modular invariance. Okay, so the modular invariance is the following idea. So let me remind you that we have been considering two-dimensional torus with a metric which look like that, modulo some overall constant. Maybe there was a factor 4 or something like that. And then this torus was obtained by periodically identifying coordinate on complex plane And then one way to think about that is to consider a lattice on two-dimensional plane like this. Okay, so let me try to explain what this is. So this point is 1, this is 0, this is 2, this is 3. Can you read that? Can you read that on Caltech side? Okay?
Yes.
Good. So this is tau plus 1, this is tau plus 2, etc. This is tau minus 1. Okay? So one way, and then we say that the torus is defined by first paying attention, focusing our attention to this parallelogram, and then periodically identifying the side, namely that we identify this side with this side, and identify this side with this side. But there is yet another way to think about that, which is first we consider the lattice defined by the following: n plus m tau, where n and m are integers. This lattice, let's see if I have some other color chalk. This lattice lambda, this lattice point lambda, are these points here. Okay, so then we can say that this torus is the same as this two-dimensional complex plane, but divide this two-dimensional complex plane by translation by this lattice. We can see that because, for example, suppose you pick some point here on the complex plane. You can pick any point, but suppose I pick this point here. By lattice translation, by linear combination of these functions, these numbers, we can identify this point with this point, and this point over here. You can show that by using this translation by this lattice, you can bring any point on the torus back into this parallelogram. So when we say that we divide the complex plane by the lattice, what it means is that we can bring any point on the complex plane inside of this parallelogram. We have to be a little bit careful when I said inside, because there is some subtlety on the boundary of the cylinder. Because on the boundary of the cylinder, this point right here is identified with this point right here too. This point right here is identified with this point right here because they differ by translation by 1. These 2 points differ by translation by tau. So, but this is exactly what we wanted to do when we construct torus out of parallelogram, because we started with parallelogram and pairwisely identify the side to obtain the torus. So we see that this operation precisely gives you the operation that led to the construction of torus. So we can think of torus as dividing the space obtained by dividing complex plane by translation by some lattice. In this case, this complex coordinate on the complex plane gave you natural complex coordinate on the torus. But we can have a slightly different view on the subject. We can introduce different sets of coordinates. Since the study of Riemannian geometry we can do independently of choice of coordinate, so we can consider the slightly different coordinate. That is the following. So here, this z initially was related to this rectangular coordinate, the coordinate x and y, which diagonalize this metric. But instead, let's try introducing the following coordinate. U plus tau v, okay, where u and v are real coordinates. So we choose u and v to be coordinates. But then with respect to these coordinates, what does this lattice translation mean? Well, z goes to z plus 1 corresponds to u goes to u plus 1. Z goes to z plus tau corresponds to v goes to v plus 1. So with respect to this coordinate u and v, the lattice translation just corresponds to shifting u by 1 or v by 1. So the lattice in question now becomes rectangular lattice. Not square lattice, excuse me. So rather than this kind of slanted lattice, we can consider this so this square lattice like this. So we are considering this torus not as a complex plane. Excuse me, this is. Let me do it again. U, V. So this is 0, 0. This is 1, 0. This is 2, 0. This is 0, 1. This is 1, 1, etc. So the lattice we are considering now is this square lattice. And then the torus viewed with this lattice just corresponds to R2 divided by this square lattice. Okay? But where does this information about the modulus tau go? Well, it went into describing the metric. Because if you substitute this coordinate z into the metric, then the metric now takes this form. Right? Or we can write it as du plus tau dv absolute value squared. Or we can write it as du squared plus twice real part of tau du dv plus absolute value tau square of dv square. So we see that with respect to this coordinate u and v, the metric is not diagonal. But you have this off-diagonal piece to this metric. And also the diagonal piece here and here are different. So with respect to this coordinate, instead of sticking to this diagonal form of the metric and changing the shape of the lattice as we change the value of tau, here we stick to a given lattice and then modify the shape of the metric as we vary it. Okay? Now, I'm introducing this new set of coordinates because this is the appropriate one when we discuss modular invariance. Yes, please. Yes. So the question was the following: that suppose you change tau, do we still have the same torus topology but with different metric? So the answer is yes. So you can see that here, for example, we are using the same set of coordinate u and v. Choice of coordinate u and v is now independent of the choice of tau, but now the shape of the metric is changing. With respect to this coordinate, the metric now is of this form. Right? So as you vary tau, so you can think of tau as parameter of the metric in 2 dimensions. Right? But now, modular invariance, so that's a very good point that you made, because the modular invariance is a question of when do 2 different tau give you same equivalent Riemannian structure. Namely, it is true that tau is parameterizing the metric, but it may be that two different tau, which seemingly give you different metric, may actually correspond to the same Riemannian structure because, after all, the metric component does not tell you precisely what the metric is because you can make change of coordinate. So you can ask, well, is there a way to change coordinate to relate different tau? And in fact, it is possible. So let's discuss the possibility of making change of coordinate with the possibility of identifying different value of tau, which gives rise to the same Riemannian structure. So, for example, suppose I do the following. So you start with this coordinate u and v. That's what we started with. But now, suppose I introduce a new set of coordinate, uv to u prime, v prime, so that u prime is equal to u plus v, and v prime is v. Okay? Now, so we have a new set of coordinates, but actually the periodicity does not change. The periodicity does not change because, so initially we had this periodic identification of u goes to u plus 1, v goes to v plus 1. So there are two periodic identification. Now, with this new coordinate, this corresponds to u prime, v prime goes to u prime plus 1, v prime. And this one corresponds to u prime, v prime goes to u prime plus 1, v prime plus 1. So you may think that, well, this gives you different lattice structure. But in fact, this lattice and this lattice are equivalent. This lattice translation and this lattice translations are equivalent. The way to see it is the following. So in the original coordinate, you had u and v, right? And then we had two fundamental vectors. One is the vector with component 1, 0. And then the other is a vector with component 0, 1. You can easily see that if you start with these two vectors and consider arbitrary linear combination with integer coefficient, then we can generate that square lattice, obviously. So this generates this square lattice. That's easy to see. Now, suppose we have different coordinates, u prime, v prime. But now, suppose we have also different basis vector. One is 1, 0, just like this vector that generates this translation. And the other is 1, 1. That generates this vector. It is very easy to show that this also generates, the integer linear combination of this also generates the square lattice. Okay, so it's easy to show why it is. Because I want to show that these two lattices are equivalent. It is because the following. Well, one can easily see that you can construct this out of integer linear combination of these, right? This plus this is this one. But conversely, you can construct, for example, this one by integer linear combination of this. Basically, this minus this gives you this one. So that means that the lattice generated by integer linear combination of these is a square lattice, but the lattice generated by these with integer coefficient also is the same lattice. Right? So therefore, this gives you the same periodic identification. But suppose I substitute this new change of coordinate into this metric. Previously, we had this metric, du plus tau dv, absolute value square. But now, u, so suppose I say that u is equal to u prime minus v prime, and v is equal to v prime, according to this change of variable. Then this is equal to du prime plus tau minus 1 of dv prime. Okay? So we have this kind of metric now. Metric parameterized by tau minus 1 rather than tau. But uv and u prime v prime are the same kind of coordinate because they are both obtained by dividing R2 by the square lattice. So that means that tau and tau minus 1 and therefore tau plus 1 gives equivalent Riemannian structure. Okay? So if you are interested in Riemannian structure, if you are interested in property of the geometric property of torus, which is sort of independent of choice of coordinate, but just depends on the Riemannian structure, then tau and tau plus 1 gives you the same torus. Yeah. Okay, well, that's another way to understand it. Okay, so now I'm going to give you one more operation that maps this lattice into the same lattice. So I'm going to the left of the blackboard. Okay, so now suppose, so previously we considered UV into U plus V, right? So that translated, this transformation turned the square lattice into the square lattice here. There is another transformation we can consider, which is exchange U and V. But for some convenience, exchange with sign, so V minus U. This obviously also maps the square lattice into square lattice. Because what one is doing is just exchange U and V. And since this is a square lattice, so exchanging U and V does not change the shape of the lattice. Okay, but now how does the metric look like? Well, the metric now becomes of the following form. Initially, the metric was like this. But now, after transformation, it becomes dv minus tau du. This is not quite this form because here the coefficient of u was equal to 1. So we can rescale the metric. We can factorize absolute value tau square in front, and then write du minus 1 over tau dv absolute value squared. So you see that if you allow yourself to multiply if you allow yourself to rescale the metric, this exchange of v and u also bring metric into this kind of metric with transformation of tau into minus 1 over tau. So this does not give you the same Riemannian structure because now the metric is multiplied by some factor. But if you allow yourself to do scale transformation, then these two gives you the same kind of metric. So here is a statement. Tau goes to tau plus 1 gives the same matrix. Tau goes to minus 1 over tau gives the same metric after rescaling. Here the rescaling is by the multiplication of the factor tau squared. So if you allow yourself to do the rescaling of the metric, then we can have both of these as a symmetry. In fact, in the problem that we were discussing today, which is to solve the Laplace equation with source, we can have both of these symmetries. That is, that equation that we were discussing, del z bar of Green's function with some local singularity like that. This problem is scale invariant. That is that if you, so when we discuss this equation today, I assume that metric is of this form with this normalization 1. But I said that we could have discussed this metric, we could have done this discussion with some additional scale factor over here. And I said that this won't change our discussion very much. And the reason for that is that the equation like this is scale invariant. If you rescale metric, left-hand side and right-hand side get scaled in the same way. So therefore, this problem of finding Green's function has both of these symmetries. In fact, this symmetry is very important. This symmetry is called scale invariance. But this is a part of what is called conformal invariance. And for example, when we discuss various condensed matter physics phenomena at criticality, conformal symmetry shows up. And so if you have such a system, say on the torus, then such a system should exhibit both of these properties. One can show that these two transformations, tau goes to tau plus 1 and tau goes to minus 1 over tau, generate the entire symmetry that are related, that relate metrics, two different metrics modulo rescaling. So most general transformation is of this form. Where this matrix A, B, C, D belongs to SL to Z. And then this is called the modular transformation. So our problem has modular invariance because of the scale invariance. Because of that, one should expect that the ingredient, the Green's function that we have written, should have nice property under modular transformation. And indeed, one can show that it is the case. So earlier, I wrote this. Somebody asked the question on this side?
I believe you want a D on the bottom of that fraction for the conformal transformation.
Say, which part of the equation are you talking about? Oh, yeah, D. Yeah, thank you very much. Okay, so I'm very happy to hear that you can see this equation clearly from their side. Are you satisfied?
Yes.
Okay, thank you very much. So look like you can see this equation very well from the other side. So, so I wrote this Green's function solution to this equation in terms of theta functions and eta functions. And then something else that has to do with subtracting the charge, absorbing the charge. But we see that this, but this term can also be discussed in the same way. But this Dedekind function, for example, transforms nicely under both of these modular transformation. The first property is sort of trivial consequence of the fact that eta function is expressed as in terms of this infinite product. because basically it is modulo this the fractional power in front. Everything else is sort of integer power of q, and since q is equal to e to the 2 pi I tau, so obviously eta function has this symmetry. It is highly non-trivial to prove this second modular transformation properties. Similarly, the theta 1 that we have over here also transforms nicely under modular transformation. It's written on my note, and so you can look at that. Okay, so we see that this modular transformation preserves this form of the solution to the Green's function, therefore. Now I'm going to the left part of the blackboard. Now, so I have about 20 minutes left, and I have a couple of things that I want to discuss before I end. One is the relation of these theta functions to the elliptic integral. Historically, actually, the problem of elliptic integral emerged before people start discussing theta function. Elliptic integral, of course, emerged from an attempt to try to find the integral to evaluate the arc length of ellipse. And people discovered that you cannot do that. You cannot do this integral. You cannot find the arc length of the ellipse using the elementary functions. So one had to invent some new functions. So that led to the study of elliptic integrals. And then it was the insight of Abel and also Jacobi that it is actually interesting to look at inverse function of this elliptic integral. And that led to the discovery of the theta function that we just talked about. So that was the way history went, but we are going in the backward direction. So let's start with this theta function and try to work our way to derive the elliptic integral. So we had this theta function, the Jacobi's theta function. From that, I'm going to introduce what is called Weierstrass elliptic function, or sometimes called Pei function. Pei is P in German. So basically, it's a second logarithmic derivative of this theta function, theta 1, modulo some constant term. This constant term is just a logarithmic derivative of the eta function. Okay? So this is called Weierstrass function. Okay? This function has a double pole at z equals 0. So Pei of z behaves like 1 over z squared as z goes to 0. As you can see from here, because theta 1 is a series of sine function in z. So therefore, it has 0 at z equals 0. So you have log of z. And then we are taking two derivatives of log of z. So that gives you double pole at z equals 0. But otherwise, this Pei function is completely periodic on torus. So you can think of this Pei function as completely periodic holomorphic function, except that it has a double pole at z equals 0. So one can also consider derivatives of p function. So for example, you can consider p prime, where that obviously has a triple pole. And then obviously this is also periodic, etc. But then there is a very important fact that comes to the following. That is that one can prove that any doubly periodic function on torus, doubly periodic holomorphic function on torus, can be expressed as a rational function of these two. Any periodic rational function periodic meromorphic function, excuse me, that is, that give me any function f that is periodic on torus, that is f of z plus 1 is f of z plus tau is f of z, and it may have pole or zeros. You can show that we can construct this as sum of the ratios of sum of product of p and p prime. And the reason that something like that happens is the following. The basic fact is that if you have a torus, which is sort of compact space, and if you have a function that has no pole, no singularities, and if it is holomorphic, then f must be constant. You can show that but this is sort of a generalization of Liouville theorem that you might have done in your course in complex analysis, that if you have a function which is not singular and it is holomorphic on compact space, then it has to be constant. So that means that if you have two functions, f1 of z and f2 of z, and if they have the same zeros, same pole, then if I consider ratio, this is an entirely smooth function. Since this has to be constant, these two functions has to be proportional to each other. So that means that if you give me any function, if I can engineer so that its poles and zero can be mimicked by p and p prime, then these two functions has to be the same. So that's a sort of proof of this statement. So in particular, there is actually algebraic relations between p and p prime. You can prove by using this line of logic that if you can construct two functions that have the same pole and same zeros at the same place, these two functions have to be proportional to each other. you can use that logic to prove that p prime of z squared is equal to pz minus E1, pz minus E2, pz minus E3, where E1, E2, E3 are special value of p function. E1 is a p function evaluated at half point, like that. So this is actually not so difficult to prove, that you just need to show that both hand side has the same whole structure. Okay? But this is an interesting equation. So for example, you see that if you write x is equal to p prime and y is equal to, or the other way around, if you write y is equal to p prime and if you write x to be p, then this means that you have this algebraic equation. Right? So if you think of y as a function of x, it has a square root singularity. So if I consider space of x, then it has a cut at E1, E2, E3. So we can, for example, introduce this kind of cut, and then the other cut goes to infinity. So if you think of y as a function of x, then naturally we have this kind of structure. But since you have square root, so that means that we have to introduce two Riemann seats, and then they have to be glued together. But since this branch cut is going to infinity, so it is difficult to imagine. So suppose you compactify this two-dimensional space by using stereographic projection onto two-dimensional sphere. So we have two copies of two-dimensional sphere with two branch cuts. This is E1, E2, E3, infinity. So since these are branch cuts, so that means that if you come in this way, you will come out this way. And you can go backward too. If you go in this way, you will come out this way. How does that entire space look like? Torus. That's right. So this is another way. This is actually, so you see that from this, that entire space looks like torus. So this property of pay function knows that it came from torus. That this is another way to understand the torus, that is the solution to this algebraic equation. Now, coming back to the elliptic integral, I'm going to the left side of the blackboard. So I said that pay function satisfies this equation. So that means that I can take square root of this to write this into this way. Left hand side is a derivative of pay function, so we can write it as dp dz. So that means that dz is equal to dp square root of p minus E1, p minus E2, p minus E3. Now you see that by integrating both hand sides, we see z is equal to an integral, indefinite integral of this. Up to constant. Now this is the elliptic integral. So this is actually what people have had before they went to theta functions. They try to understand the way to evaluate arc length of ellipse. And then they obtained an integral of this type. And then they tried to understand the behavior of this integral and discovered some mysterious multiperiodicity like this. And then it was an insight of Arbero and Jacobi that, well, actually, this kind of mysterious property can be sort of made, clarified much better if you consider inverse of this function. So here we are considering z. So when we consider elliptic integral, we are considering coordinate z as a function of p. It is just as if, this is a correspondence between this torus as a fundamental domain as a parallelogram. So z is a coordinate here. And pay, y/pay and pay prime are algebraic coordinate like that. So this elliptic integral sort of relate this algebraic coordinate pay with this coordinate z. But in this way, you can invert that and write pay as a function of z, but then this pay is expressed in terms of logarithmic derivative of theta function. So that led to theta function. So today in this lecture, I went in the opposite direction. That is, that we started out trying to solve the Laplace equation on torus in this parallelogram coordinate z, and then discuss the theta function, and then introduce this pay function and discuss its algebraic relationship like that, which leads to this elliptic integral. The history of mathematics went backwards. They started out with this elliptic integral and then discovered the theta function and geometry of torus. You can see that we can discuss this kind of story for any Riemann surface. So Riemann surface was initially introduced to try to understand this kind of uniformization problem. That is that when you have a function with branch cut, it is not natural to just consider this as a function on a single complex plane. But for example, in this case, you should consider double cover of complex plane, which turned out to have the same geometry as a torus. You can consider more sort of interesting combination of branch cuts to consider other geometries. For example, one can easily imagine a more complicated equation like y squared is equal to I equal 1 to 2g plus 1 of z minus ei, where ei's are some constant. So in this case, what you have is two copies of sphere with 2g plus 1 branch cuts. 1, 2, 2g plus 1, 1, 2, 2g plus 1. And then you try to sort of, oh, no, I didn't say it correctly. So the number of branch cuts is g plus 1. And then you try to sort of pairwisely identify this branch cut. Then what you obtain is two-dimensional surface with g handles. So this gives rise to a special case of so-called Riemann surface of genus G. So then we can repeat the stories that we had today for Riemann surface of higher genus, namely more handles. So for example, we can discuss theta functions and discuss the solution to Laplace equation with sources on general Riemann surface expressed in terms of these theta function for higher genus Riemann surfaces, etc. But since I just ran out of time, so I should stop here. So I should make a couple of announcements. I think I gave out the homework problem set earlier, so that is due soon. And for Caltech student, this is the end of this term. So I hope you'll have a nice winter vacation. If you have any questions from you guys, let me know. Or I'm going to be back to Caltech Monday next week, so you can ask me in person also. For University of Tokyo student,